A Chinese data center has just deployed a new AI chip that is being described as up to 1,000 times more efficient than Nvidia GPUs for specific workloads. Not in a lab, not as a prototype, but in real operational environments right now. When this information first circulated a few days ago, many observers assumed it was exaggerated marketing. China has announced breakthroughs before, often ahead of verification. This time, the situation is different. The chip in question was awarded the Leading Technology Award at the World Internet Conference 2025 in Wuzhen, selected among more than 400 candidates from 34 countries. That alone does not prove technical supremacy, but it justifies closer inspection. So let's slow down and look at what this chip actually is, what it is not, and why it matters regardless of the headlines. The processor was developed by ChipX, a research institute based in Wuxi, affiliated with Shanghai Jiaotong University, in partnership with a startup called Turing Quantum. The core idea is simple but powerful. Instead of moving information using electricity, like traditional CPUs and GPUs, this chip processes data using light. Photons travel through more than 1,000 integrated optical components embedded on a 15-centimeter silicon wafer. Why does that matter? Because photons do not generate heat the way electrons do. Because light can carry more information per unit of energy. And because optical signals suffer far less resistance and loss than electrical ones. In modern data centers, energy has become the limiting factor. According to the International Energy Agency, some facilities already spend more on electricity than on hardware, and global data center energy consumption is projected to double by 2030. This is the problem every major AI company is trying to solve. Now here's where the narrative becomes controversial. Several Western experts, including analysts from Post-Quantum, a company specialized in quantum security, reviewed ChipX's published technical papers. Their conclusion is consistent and clear. This is not a quantum processor in the strict scientific sense. There are no single-photon sources, no quantum entanglement, no quantum superposition in the computational model. Technically, this is a classical photonic accelerator. Highly advanced, but not a quantum computer. So why is it being labeled quantum? Part of the answer is linguistic. In Chinese popular science media, the terms photonic and quantum are often used interchangeably. Another part is branding. When your partner company is called Turing Quantum, the label tends to propagate. This phenomenon already has a name: quantum washing. The use of quantum terminology to attract attention, funding, and political interest. But dismissing this chip as mere hype would be a mistake. Even critics of the marketing narrative agree on one point: the engineering achievement is real. Integrating more than 1,000 optical components on a single silicon wafer, synchronizing them, and making them manufacturable at scale is extremely difficult. Very few organizations worldwide can do this. And this leads to the most important part of the announcement: industrialization. In June 2025, ChipX launched China's first pilot production line for thin-film photonic wafers of 15 centimeters. The line can produce approximately 12,000 wafers per year. Each wafer yields roughly 350 chips. Compared to classical semiconductor fabs, this is modest. But for advanced photonic processors, this represents a major step toward mass production. More importantly, ChipX claims to have closed the full industrial loop. Design, fabrication, packaging, testing, and system integration are all handled within the same ecosystem. According to the company, systems that previously required 6 months to assemble can now be deployed in less than 2 weeks. That kind of timeline compression is what separates laboratory research from deployable infrastructure. Now let's place this in a global context. In the United States, the startup Quantum raised $1 billion in September 2025 to build large-scale photonic quantum computers targeting 1 million qubits. Nvidia is an investor, and is actively collaborating on GPU-QPU integration. Quantum manufactures its chips at global foundries in New York on 300mm wafers and plans operational quantum data centers in Chicago and Brisbane by 2027. In Europe, companies like Photonics in the Netherlands are working on smaller 10-centimeter wafers, focusing on specialized photonic integration. Meanwhile, Google and IBM continue to pursue superconducting qubits. Microsoft recently unveiled its Majorana-based topological qubit architecture. No one has won this race yet. What makes the Chinese announcement notable is not theoretical ambition, but deployment claims. ChipX states that its photonic processors are already suitable for aerospace simulations, biomedical modeling, and financial computation, fields where large-scale matrix operations dominate. The architecture is designed to scale by stacking chips in a manner similar to modern GPU clusters. In theory, this could reach processing capacities equivalent to millions of quantum-inspired operations, while maintaining low power consumption due to minimal heat generation. Now we need to address the headline number: 1,000 times faster than Nvidia GPUs. This figure does not come from direct benchmarks on identical AI workloads. It appears to be derived from a combination of energy efficiency per operation, latency on specific optical circuits, and comparisons against CPUs rather than modern GPUs. For certain tasks, especially matrix multiplication, photonic systems can indeed show massive gains. This is the same reason GPUs originally replaced CPUs for deep learning. But this is not a universal replacement. This chip is not 1,000 times faster for everything. Even Nvidia's CEO, Jensen Huang, stated in January that useful general-purpose quantum computing remains 15 to 30 years away. At the same time, Nvidia is investing heavily in photonics, quantum integration, and 800-volt power architectures, because Nvidia understands the real bottleneck: energy. In Virginia alone, data centers already consume roughly 26% of the state's electricity. Across the United States, they represented about 4% of national electricity consumption in 2024. By late 2025, that figure has almost certainly increased significantly. So what should we take away from all this? China has demonstrated the ability to industrialize advanced photonic chips faster than Western competitors. This is not full quantum computing, but it is a foundational technology for it. The same components used in classical photonic accelerators are also used in true photonic quantum architectures. The boundary between classical and quantum photonics is thinner than it appears. Another key lesson is strategic communication. Labeling something as quantum attracts political attention, investor capital, and public interest. This is not unique to China. But in a technology race, perception increasingly shapes funding and momentum. For those working with AI today, the message is clear. The future of AI hardware will not belong exclusively to GPUs. Photonic accelerators, hybrid systems, and quantum-inspired architectures will progressively enter the ecosystem. And those who understand how these systems work will hold a real advantage. Not tomorrow, but sooner than most people expect. This transmission ends here. The next one is already forming. Stay aware and subscribe to Remain in the Signal.